Good evening, ladies and gentlemen, wherever you are. My name is Hussein Al Ali, and going over a module on reliability in design for Relic, your partner in reliability. In this module, ladies and gentlemen, we will cover the following topics. We will talk about key terms and definitions. Then briefly, why reliability? And then we go over the definitions of reliability, maintainability, and availability. We will talk about the famous bathtub curve. We will show how to calculate the mean time between failure. We will talk about reliability distribution, and again, calculating reliability. We'll talk about reliability block diagram, asset lifecycle cost, reliability approach in design, and we'll finish with some question sessions. Talking about key terms and definitions, starting with availability. Availability is defined as the probability that an asset is capable of performing its intended function satisfactorily when needed in a stated environment. Definition of failure is the loss of an asset's ability to perform its required function. It does not require the asset to be inoperable. The failure could also mean reduced speed or not meeting operational or quality requirements. Definition of failure rate, designated by FR, is the number of failures of an asset over a period of time per unit measurement of life. Failure rate is considered constant over the useful life of an asset. We will explain later what do you mean by the useful life of an asset. It is normally expressed as the number of failures per unit time, and even just as important, it is the inverse of mean time between failure. And the failure rate is usually denoted by the Greek symbol lambda. Mean time between failures. Mean, whenever you see mean, ladies and gentlemen, mean means average. So mean time between failures, this is the basic measure of asset reliability. It is calculated by dividing the total operating time of the asset by the number of failures in the same period of time. MTBF is the inverse of failure rate. Mean time to repair, meaning average time to repair. This is the average time needed to restore an asset to its full operational condition upon a failure. MTTR is the time to repair the asset and is an important measure of maintainability. Definition of maintainability. This represents the ease and the speed of repair and maintenance actions with which an asset can be restored to operating condition following a failure. It is measured by MTTR. Reliability, defined as the probability that a system will perform its intended function satisfactorily for a specified period of time under stated conditions. It is usually expressed as a percentage and measured by the mean time between failures. Reliability-centered maintenance, RCM. This is a systematic and structured process to develop an efficient and effective maintenance plan for an asset to minimize the probability of failures. The process ensures safety and mission compliance. Uptime. Uptime is defined as the time during which an asset or system is either fully operational or is ready to perform its intended function. And it is the opposite of downtime. Why do we need to focus on reliability? Why is there so much attention, focus, demand for reliability? Well, every business needs to have customer satisfaction. And without reliability, you will not achieve customer satisfaction. Why? Because basically, you will not be considered as a reliable partner. Your delivery pattern can be out of control. Quality of your product can be out of control, and your reputation is affected. Customers will not be satisfied. So as far as the business is concerned, they need to focus on reliability to maintain long-lasting customer satisfaction. Also maintain long-lasting reputation. Good reliability have reduced operation and maintenance costs, which is what every business wants. Repeat business, and it gives the organization competitive advantage. These definitions now expressed in formulas. Reliability, as explained earlier when we went over the definition, is very much related to the MTBF, the mean time between failure. And a larger MTBF generally indicates more reliable asset or component. Reliability is calculated by the formula RT equal the logarithmic E, constant E, to the power of minus lambda multiplied by T. Lambda here, ladies and gentlemen, is the failure rate, which is the inverse of the mean time between failure. Definition of maintainability, as we read earlier, the same as we read earlier, and maintainability is usually expressed in hours by mean time to repair, sometimes by mean downtime. And MTTR is the average time to repair assets. It is pure repair time, called by some wrench time. Definition is as defined earlier of availability. The availability may be stated as the probability that an asset will be in operating condition when needed, How was it calculated? In two ways, either MTBF divided by MTBF plus MTTR, also by calculating the uptime, dividing it by the total uptime as well as plus the downtime. Both ways gives you the same answer in percentage. Now we'll spend a few minutes to talk about the famous bathtub curve. The bathtub curve is widely used in reliability engineering, and the curve describes a particular form of the hazard function which comprises three parts. The first part is a decreasing failure rate, known as early failures or infant mortality, similar to our childhood. Young parents in particular realize this when they bringing their newborn child with a lot of bad night sleeps, too much crying. They don't know what it is, but a lot of difficulties during the first few months before the child adjusts to the normal life situation. Similarly, with the start of a new plant, there is, as is described here in region A, the break-in phase, and the failure rate starts high and it gradually settles down to more or less a reasonable pace in the middle life phase of region B, which is the second part of the bathtub curve. This is generally, by and large, a constant failure rate, known as random failures. It's again similar to our adult life. This region B is what is considered the useful life of the asset. And the third part of the bathtub curve is an increasing failure rate known as the wear-out failures, similar to old age. Why it's called bathtub curve? Because the graph itself resembles the shape of a bath. More explanation of this. Section A, the infant mortality, is designated by decreasing failure rate, and it may be these failures resulting from manufacturing escapes, workmanship, handling, process control, materials issues, contamination, improper installation. So many reasons that have failures at this stage until people get used to it, and the assets also get used to the raw material that is being processed and to the environmental condition, the operating condition, the maintenance conditions. Then things start to settle into a more or less stable phase called the useful life. And the failures here, as I said, it's more or less constant failure rate. Failures could be due to external environment, system interactions, insufficient safety factors in the design, higher than expected random loads, maybe due to human errors, and maybe due to misapplication. Phase C is the wear out, designated by increasing failures, but at an exponential rate. As time goes by, more and more of these failures occur. It changes over time. This is as a result of wear out, aging, degradation in strength, materials fatigue, creep, corrosion, poor maintenance, many reasons, but that's what happens to normal assets. Now we explain about mean time between failure, MTBF. The mean life during which all parts perform within their specified limits during a particular measurement interval under stated conditions. Ladies and gentlemen, always note that this is under stated conditions. What do we mean by this? It has been repeated under availability. It has been repeated under reliability. It is being repeated under MTBF. What it means is to within the design limits of the asset. So if the asset is designed to deliver a certain flow rate at a certain pressure, at a certain temperature, at a certain atmospheric pressure, if you change these criterias, then you're not utilizing the asset under the stated design conditions. So if the plant decides to increase the throughput beyond its design rate, then of course the reliability will be affected, and vice versa. This is the most common measurement used to assess reliability. So when you say high MTBF means high reliability. Low MTBF means low reliability. And the mean time between failure in a graphic format, you see that the machine runs and then you have a failure. And then machines runs for a longer time this time, and then you have a failure. And again, it goes and run. So you calculate the running times over a period of time and divide that total, the summation of the running time over the number of the failures to be able to find the MTBF over that particular time. So to calculate MTBF, it's the summation of the operating time over the number of failures. MTBF then is summation of time to failure over the number of failure. Now let's talk about the probability distribution. Binomial distribution, Poisson distribution, normal distribution, log normal distribution, exponential distribution, gamma distribution, X2 distribution, Weibull distribution, and extreme value distributions. People who study statistics are more familiar with these. We will talk about 2 or 3 of these distributions that are most commonly used in our work in the reliability field. The exponential distribution is one of the most common distributions used to describe the reliability of an asset or a component in a system. It models an asset or component with the constant failure rate, the middle section of the bathtub curve. Most of the assets, consumer or industrial, follow the constant life rate for their useful life. So exponential distribution is widely used to estimate the reliability. And the basic equation for estimating reliability is RT equal E to the minus of lambda multiplied by time. And lambda is defined by the failure rate which is equivalent to 1 over MTBF. T is the mission time in cycles, hours, miles, etc. E is the base of the natural logarithm, which is a constant equaling 2.71828. So basically, by knowing the MTBF, you can find reliability, because after you find MTBF, you take the inverse of it, which is lambda, and then you have everything in your hand to be able to calculate reliability. We will share some examples to illustrate. Example here, a hydraulic system which supports a machining center has operated 3,600 hours in the last 2 years. The plant CMMS system indicated that there were 12 failures during this period. What is the reliability of this hydraulic system if it is required to operate for 20 hours or for 100 hours? So 2 calculations is required, one for 20 hours and one for 100 hours. First thing is we have to calculate the MTBF, and the MTBF is the total operating time over the number of failures, which in our case is 3,600 hours divided by 12, and that's equal 300 hours. So that asset, that hydraulic system, has had an average time between failures of 300 hours. The failure rate is the reciprocal inverse of MTBF. 1 over MTBF, 1 over 300 is 0.003334 per hour. And the reliability for 20 hours, then you multiply this lambda by 20. And hence, for 20 hours, you get the reliability in a percentage as 93.54. And then, if you want to know the reliability for 100 hours of operations, all you have to do is change the T from 20 to 100, and that gives you 71.65 reliability. Another example here. A plant's air compressor system operated for 1,000 hours last year, and the plant CMMS system provided the following data. Note that every time we refer to using the information from the CMMS system. So operating time, 1,000 hours, number of failures, 10, total hours of repair time, 50. Calculate MTBF, 1,000 over 1 over 10. So the MTBF is 100. Calculate MTTR, total repair time 50, and we have 10 failures. 50 over 10 is 5. Calculate availability. Calculation of availability is MTBF divided by MTBF plus MTTR, or uptime divided by uptime plus downtime. And then you calculate reliability for 20 hours and calculate reliability for 100 hours, as the example that we looked at previously. Now, reliability block diagram, RBD. The failure logic of an asset, components, or a group of assets and components called a system can be shown as a reliability block diagram. This diagram shows logical connections among the systems, components, and assets. And reliability block diagram is not necessarily the same as a schematic diagram of the system's functional layout. The system is usually made of several components and assets which may be either in series or parallel. So components or assets can either be in series or in parallel. What is the meaning of series? What is the meaning of parallel? Series mean that for the system to function, all the components in the series connection must operate. Parallel mean even if one equipment is down, as long as the other is functioning, then the system operates. But in reality, you usually have a combination configurations to provide us the desired inherent reliability. Now, the way to calculate reliability in series connection is you find the reliability of each component and you multiply it by the reliability of the other components and so on. So in this case, where we have two components in series, the reliability of the system is R1 by R2. So you calculate the reliability for the first component in percentage, and you calculate the reliability of the second component, and you multiply them together. Reliability in active redundancy or parallel system, the way to calculate it is a little bit different than that one. Two ways. It's either 1 minus R3 multiplied by 1 minus R4, or R3 plus R4 minus R3 multiplied by R4. Either way, you get the same answer. If you, and you will have combinations like these, you configure what is in parallel and you calculate the reliability of the parallel components first, and then you find the reliability of the complete system as shown here. Would be a good idea to take a photo shoot of this and do the calculation to find the reliability of the system. Another practical exercise. A plant's air compressor system operated for 1,000 hours last year, and the plant CMMS system provided the following data on this system. Operating time 1,000 hours, number of failures 10, total hours of repair time 50. So again, calculating MTBF 1,000 over 10 equals 100. Calculating MTTR 50 over 10 equal 5. Calculating availability, then calculate reliability for 20 hours, calculate reliability for 100 hours. More practical exercise that I suggest you do at your leisure. Take a photo shoot of this and apply what you learned in the formula for calculating the reliability for the series components and the reliability for the reliable components. Now we talk about reliability block diagram. A block diagram representation of a system is shown below. Overall system reliability, then first we said you do work out the parallel components and then apply the formula for the series to find the reliability of the system as a whole. Again, another useful idea to take a caption of this and go over the calculation to get yourself some experience in doing it. Of course, in real life situation, The RBD is much more complicated than the examples we looked at, as you can see here, or here. It's a more complex module, or here. Again, you can see in real life situation what it means to eventually find the inherent design of the complete system, the inherent reliability of the complete system. Now we talk about asset lifecycle cost. What do we mean by asset lifecycle cost? Life cycle means all the way from initiation to disposal of the asset or the plant. And we take the cost of each individual phase. So we take, for example, the cost of the initial cost, meaning how much did this cost us on capital to buy and install and commission and start up the plant. Then there is some service cost, there is the preventive maintenance cost, there is operating cost. We take all of that in consideration all the way until the plant is ready for disposal. And there is also some disposal cost that we need to bear in mind. We add all these together, this becomes the total life cycle cost. Okay. I'll go over this again. Design and development of the plant is about 5 to 10%. Production, fabrication, installation is about 10 to 20%. Then the biggest chunk of the cost is in their operations and maintenance, O&M phase, and that is 65 to 85%. Disposal for most plant is less than 5%. The only big exception for this is if we're looking at nuclear type industry, where the disposal cost can be greatly much more expensive than the 5% here. Very hard to tell how much it will actually cost. People are still wanting to figure out the best way to get rid of nuclear waste. So in a graphical format, you can see that the acquisition, that is the capital cost of buying and running and starting the project, although very expensive, but in comparison to the operation and maintenance, it's only a small mountain. Big mountain is here, operation and maintenance. And this here is the disposal cost. See, by realizing this, we know that if we spend a little bit more in here to improve the reliability and functionality and the design for this phase, this small expenditure will have a much more significant impact during the operation and maintenance phase. In order to develop a reliable asset, there must be good reliability requirements and specifications. Key elements of reliability specifications: probability of successful performance, function, mission to be performed, usage time, operating conditions, environment, skill of operators and maintainers. It has been found that as much as 60% of failures and safety issues can be prevented by making changes in design. So assets must be designed for fault tolerance, designed to fail safely, designed with early warning of the failure to the user, built-in diagnostic system to identify fault location, designed to eliminate all or critical failure modes cost effectively if possible. The following analyses are recommended to be performed during design phase from conceptual design to final design. reliability analysis, maintainability analysis, system safety and hazard analysis, human factors engineering analysis, and logistics analysis. That brings us to the end of our presentation. We'll go quickly over some questions that start with the first one. Failure rate of a component assets can be calculated by knowing, of course, it is MTBF, and the failure rate is the inverse of MTBF. Next question, which phase of asset life cycle has the highest cost? If you remember, the big mountain was under operation and maintenance. Question number 3, how soon we can restore an asset is measured by mean time to repair, MTTR. Question number 4, availability is a function of MTBF, MTTR, uptime. Answer D is uptime and downtime, because you divide, to find availability, you divide uptime over uptime plus downtime. MTBF is measured by operating time divided by the number of failures of an asset. True or false? True. Number 6, a tool that produces a diagram that displays various conditions that could cause a particular failure is FTA, failure tree analysis. Number 7, a maintenance engineer has a list of pump failure modes and the frequency of occurrence. Which of the following diagrams can help to prioritize maintenance action? Pareto chart. What is Pareto? 80-20. It looks at what are the 20% of the problem of the faults that cause 80% of the cost or the time to the organization. So by knowing that, you spend a less amount of effort focusing on these 20% and you get much better reward. Number 8, a maintenance team observes that a new gearbox that was installed recently has failed. Further investigation revealed that the gear teeth were misaligned during installation. What category will this failure mode fall under on the bathtub care? Infant mortality, because it has been recently installed. Number 9, reliability predictions are often expressed in terms of mean time between failure or its reciprocal. The reciprocal is known as the failure rate. And the last question, if a machine is run for 500 hours and 5 failures are observed during this period, what is the mean time between failures? 500 over 5 is 100 hours. So the answer is D. Ladies and gentlemen, we come to the end of the presentation and I wish you all the best. Bye-bye. Thank you very much. For more information, you can reach us at info@erelec.com. Get in touch. We'll be happy to answer your questions. All the best and have a pleasant night. Thank you for listening. Bye.